All right, welcome everyone. Today we're going to look at our double integrals over our more general regions. Right, so we're going to look at our double integrals over our general regions, right, which is of course much more common. And we saw previously when we were introducing our double integrals that we can start off integrating over a rectangle, right? So previously we integrated, we did our double integrations, we did our iterated integrals over a rectangle. We started in the xy plane, but it could have been in any of those coordinate planes, depending on how our functions are defined. But that idea that we had some set rectangular region, we can call it R this time. So we did D last time, so that domain region, where RY, let me make sure I label this one, goes from C to D, right? So our Y variable between C and D, the X variable goes from A to B, right? So between those zones, those regions, then we would take this integral over R over that region, and we can have some surface, right, as a function of X and Y, and we call it dA, right? So we have this region, which we defined somewhere as this rectangle before, and we imagine like what we're doing. We're taking some little portion dA and measuring that kind of volume trapped inside that column underneath that surface, and we're summing up all those little columns. And so depending on our order that we want to use to integrate, we can do, right, dx dy or dy dx. We usually subtract the inner integrating factor, how we organize here. X is going to go from A to B, y is going to go from C to D. And we can do those integrals. X is a variable, y is held as a constant. Get that integral, plug in values, evaluate, get that answer, then do the integral of that answer, go to y is our variable, calculate, compute through. And whether we have dx dy or dy dx, we switch those orderings, right? We can integrate. But this is when we had a specific rectangle constants for our upper and lower boundaries, lower limits for integrals. But now, right, more commonly, we will have a region defined by a curve or intersection of curves. So that's where we're going to start to see some of our calculus 1 work in integrals, right? The area between two curves, the area trapped inside, the x-axis, y-axis, and some function, right? Intersection of curves to integrate over. Okay. So if I look at that domain space, right? So for instance, if I look at that XY plane, maybe I want to integrate over this region, right? Or maybe this is, right, the area between the x-axis and the curve given by y is equal to 4 minus x squared. Right? So if this is here, that downward facing parabola, we have our x-axis. So I want to be above the x-axis, below that curve. This is the region I want to integrate over, right? And so then in our three-dimensional space, starting to incorporate that information, we would have our region like so. Right, there's my parabola. I just kind of shifted it down. And again, we can have some surface over that region, but we're going to try to imagine those little columns of volume throughout that region to get that double interval. Okay, so we're going to want to integrate over r. Our function, right, rc is equal to f of xy dA, I'll leave it in kind of blue to mimic what we saw here, right? So we have to think about, okay, how is that dA still going to look like a dx dy, but how is that going to be in relationship here? How is that going to fit in? Okay. All right. So let's think about that. Before I worry about that function, we can evaluate. So let's think about that. Okay. All right. How can we manage that area differential and the limits of integration needed? Right? What is our x going to be between? What is y stay between? Okay. So if we look at, we'll use that same region R, okay? Underneath the parabola, above that x-axis, and we're trying to utilize that region R. Okay, let's get that straightened up. So how can we build this up? So again, what I'm thinking about, if I look at my picture here again, right? I'm thinking about, we're going to have these little pieces of area, TA, right? That we're going to use as the basis of those columns that we're going to send up to get that volume, right? So as we go through, when we talked about like our partial derivative work and kind of related that to doing this double integration, that we kind of held a variable constant and see how does the other variable change throughout. Okay. So we start to put this through. I'm going to start to organize here with this curve, with our function here, right? These boundary points, that's going to point at -2, 0, 2, 0. This point up here is at 0, 4, that vertex of parabola. Right? And so looking at it, well, along this x-axis, the same thing as the line y equals 0. For this space, looking at those inputs, you can start saying, well, x goes between -2 and 2. Right? That's the smallest x value we can use. That's the biggest x value we can use. There's no x values outside. That's going to be a part of that region. That seems to make sense. The y value, the lowest is going to be 0. We're stopping at that x-axis. That upper value, right? Well, the biggest y we get is 4. Right? So we might start to think about, okay, well, with that, there's my y equals 0. The biggest value was 4, right? Well, here we run into some trouble. We can't always use that 4, right? Imagine choosing a particular x value. Okay, so if I take that space again, right, and again we're going between -2 to +2 on the x, that one's hopefully kind of clear. There's my region, but what if I just take this little region here, right? What happens when I pick one particular little x, like x equals 1.2 or something like that? X equals 1.4, whatever, some x here. In that case, in that rectangle, right, the lowest, the smallest y is still 0. It's still going along that baseline. But the highest y, the biggest y, it depends on what that x value is, right? The highest y is going to be, right, that y value on that curve. That's going to be the highest that y can go. It's not going to go all the way to 4. So in that case, for the highest is given by that 4 minus x squared, right? Depending on what our x, in this case 1.2, you can plug that in, compute. But for any x value it might be, the lowest y value is 0, the highest is going to be wherever the curve ends. So that starts to get us to think then for our limits on y, the lower limit will be 0 still. Lowest goes not go past that, and each of those rectangles I kind of drew started there. But the upper limit will be the curve that y equals 4 minus x squared. In particular, that expression of involving x, that 4 minus x squared, that's how, depending on what x I'm at, that's how high the y can go. So then for our limits of integration, then we had before, x was between -2 and 2. We start off fixing, okay, I can go within that range of x in particular. The y then depends on that. It goes from 0, that's the lowest point it always, and the upper part, 4 minus x squared. So then, getting back to that problem then, thinking about that, okay, if we're going to integrate over that region R of our function, then have it dA. When we do our integration, our comment here, what we see with those boundaries, I'm going to make this note here, we're going to always put the limits that are all constants, right, just numbers, as that outer integral, right, the last integral that we evaluate. So -2 to +2 was our dx. The variable limit of integration, the limit of integration involving a variable, goes for the inner. Because once we compute, we want to make sure we get a numerical final answer. We don't want any variables in the final answer. So then as we start to evaluate and we get a result, we saw our kind of solid numerical calculation with a definite integral. Now when we evaluate that upper limit, in this case, is going to be variable. And so you're going to get a variable expression to integrate. X is going to be left, so when we do our integral of dx, it'll make sense. We're going to get something that we can expand upon. Okay? So let's check out a problem. Okay? Put this together. All right. Out of the way. Let's look at a solid example to work through. We're going to evaluate the double integral. And we have here this double integral over the region D of x squared plus 2y dA, where D, that region, is bounded by the line y equals x, the curve y equals x cubed, and we keep track that x is going to be greater than or equal to 0. So it's in that first quadrant, okay? On the right side, I guess I should say more affirmatively. So when we look at, I'm not going to worry about this as my function, right? I'm not going to worry about building up that surface. I'm going to focus on that region D. So in that xy plane, x is going to be greater than or equal to 0, okay? So that means we're looking at that space. So I'm not going to worry about if any part of the graph's over here. That line y equals x. Continues outwards. Okay. Y equals x cubed. 0, 0. And it's that kind of S curve. I'm going to exaggerate that curve in. Okay. And again, it's going to continue to climb out of that. It's going to come down afterwards. But there's my y equals x cubed. And now D is the region that's bounded anything closed by. So this is just identifying that we are on this side of the x-axis, so it doesn't necessarily make a boundary. So what we're seeing when we're talking about this region interior, that's that region we're talking about. So that's your first step in these double integrals. Later on, triple integrals, imagine that. Okay, is finding that space, that region over which we're integrating. So with that, so that's kind of like where this 28 comes in, and that's the calc 1, looking at the area between two curves, right? Thinking about that. And so in that mindset, right, how would we work on finding that area? Out of habit, I think out of just kind of common practice, one thing we do is we imagine kind of drawing those little strips vertically, right? Because if I'm going to fill those in, I'm going to go to the space. And if I was going to find for that rectangle, right? Let's do this right? So imagine, consider finding the area in the region D, right? Basically between the curves, right? And thinking about that rectangle, right? The lower height is at x cubed. The upper portion is x, right? My upper and lower limit that we'll get into, right? That upper and lower height is like so. Where we are. And then, as I kind of alluded to here, x is going in between 0 and 1. Right? So in thinking about that, if I let x go between 0 and 1, anywhere I am along that x-axis, that little rectangle we can draw, the y is going to be between x cubed and x. The lower and upper boundaries for the height of that little representative angle if I was going to find that area. Okay? So then, when it comes to building up this double integral, we can rewrite it. So now with my comment from before, the component that's solely constants goes outside. 0, 1, dx. The y, the one that has the variables, goes inside x cubed and x, right? Our lower and upper. So that will be our integral. Okay? And let's evaluate that in this next component. So if I was going to integrate, okay, taking the problem, integrating with respect to y first, okay? So in that discussion, y is the variable, x is just considered a constant, just like having a number there. So when I do that integral, x squared is a constant, right? Like if I just had a 2 there, integrate, it would get the variable y. Plus, and now here, 2y, then enter derivative y squared right over 2, 2's there, goes away. So this is our antiderivative with our limits and integration, x cubed and x, right, which are going in for the y. I'll plug these in for y. That's the definite integral we're evaluating. So we're going to get here that x squared present times y plus that y being squared. I should put that in blue here. Okay. But what's that y? The upper limit x. Take away the lower. Putting the lower limit x cubed. Okay. So upper limit, take away lower limit. Evaluate here, x squared times x cubed plus x being squared minus x to the fifth power, right? Add those exponents, multiply here plus x to the sixth. Distribute the negative in, rearrange to descending order. Negative x to the sixth minus x to the fifth plus x cubed plus x squared. Right, so that's the y integral. We're getting some expression out involving only x's. So then, taking the result, integrating with respect to x now, only x is present. We shouldn't have any other variable remaining. Integrate with x, add 1, divide by the new power, negative 1/7 x to the 7th minus 1/6 x to the 6th plus 1/4 x to the 4th plus 1/2 x squared. Evaluated 1 and 0. Double check that result there, that calculation, that integration. Plug it in upper limit, 1, negative 1/7 times 1 to the 7th minus 1/6 times 1 to the 6th plus 1/4, 1 to the 4th plus 1/2, 1 squared minus, and then write all those other ones. These become 0. Plug that 1 in. So then the fraction, negative 1/7 minus 1/6 plus 1/4 plus 1/2. Doing that arithmetic, right, getting your common denominator. I'll fill that in later. We can get the LCD, plug in, identify. And in this case, because of the 7, it's going to make that denominator jump up. The 7 by 6 jump up pretty big. I think the closest is going to be 84. And we can find that. Okay, I'll do that. I'll fill that in when I post these notes later. Okay. But what I wanted to get to, right, go with that process, of course. But here, going back to our problem, and I have it, right? I took that slice, took that rectangle vertically, let x go from set constants, and figure out what y is doing. But depending on your boundary curves, depending on the orientation of your region, we could have also sliced the other direction, right? So let's do that in that setup, and we could practice evaluating and make sure we get the same exact answer. Okay, so in this case, if we go back to that quickly drawn diagram, if we have our curve here, y equals x cubed, y equals x here, we're still going between that point 0, 0 to 1, 1, right? That's where these two curves meet. This is that region D we're talking about. Okay, but what if we slice this way? Now, our little rectangle we're talking about looks like this, where this portion is that line y equals x. This portion, y equals x cubed. We're going to work from left to right, right? From smaller to bigger, lower to upper. This time, though, we can see that our y goes between 0 and 1. And anywhere we are along that y-axis, the smaller y goes from, again, x, or y, sorry, and then the upper, if y is going to be the constant, the upper needs to be a function of y, of that constant. So this is going to correspond to x equaling the cube root of y, right? Solving for x here, y equals x, x equals y. So in this case, though, what I want to kind of bring in is that the x ranges between the smaller one being the line x equals y, and the upper being the cube root of y. So when we look at that integral, we can also rewrite it. And then our function was what? X squared. Let me copy that down one more time. X squared plus 2y problem before. But now my dy on the outside going from 0 to 1. Y is going to go from 0 to 1. But now the dx is going to go between y and the cube root of y. Right? That inner variables limits of integration, they can be variable format, but they depend on the variable of the outer integrating factor. Right, so now when we integrate, X is the variable. So we're going to get here 1/3 x cubed plus 2y times x, or xy, evaluate y, cube root of y. And so now we can do our fundamental theorem of calculus, evaluate here, have an expression only involving y at the end, integrate that result with respect to y, plug in these limits, and we should get that same answer. That's right. The other calculation, that other way of organizing those limits, as we had identified here. Okay. All right. So I'll leave it at that. We'll get some practice with these and see some of these different types. I might put in some more written notes up to think of some of the properties and other regions we can manage. Okay, but definitely the best bet is going to be to get some practice in looking at those regions over which we're integrating and thinking about how those different boundary curves or oriented are being used to kind of enclose this region, and thinking about how we can deal with those limits. Okay. All right. I'll leave it at that. Questions, concerns, definitely let me know.